Hello folks, it's your old buddy and pal here, Chad Goings, Rolling Hills Consulting Services. And today I thought I would tell you a little bit about tricks you can use to create a relative elevation grid in ArcGIS. So again, my name's Chad Goings, and I work for Rolling Hills Consulting Services, and we're based out of Washington, Iowa. And you can get a hold of me at 319-461-7427. And if you purchase the data for this course, you get free tech support. You can call me or email me, and I'll give my email address at the end here, and I can take you through anything that you might not understand. So that's what I'm going to talk about today, is tricks to creating a relative elevation grid in ArcGIS. So, what is relative elevation? You might compare it with absolute elevation. So, let's say you go out to the top of a hill. That particular spot that you're standing in is going to have an absolute elevation. It might be something like 774 feet. So, it's usually something like above mean sea level or something like that. So, relative elevation takes into account an area around that particular point. So it's not an absolute elevation like 774 feet. It's a relative elevation compared to the elevations around it. So you might think of this hill here up on top, absolute elevation of 774 feet. But when you consider the area around it, you could scale it from relative elevation, you could scale it from 0 to 1 or 0 to 100%. And so if you're at the highest spot within that particular radius or area, then you would be at 100% relative elevation. And if you were down on the lowest spot within that particular radius, then you'd be at 0%. And then, you know, it would range from 0 to 100 as you would move up this hill. So that's what relative elevation is if you've never heard of it before. So, you know, why might you use a relative elevation grid, or when might you use a relative elevation grid? Places I've used them before are in predictive models. So I have another course, logistic regression course, where I used an archaeological case study for predicting where archaeological sites are. Well, if you go back here, you know, sometimes, you know, there might be a preference anyway for archaeological sites to be on the highest spot within a certain radius, or the lowest spot, or somewhere in between. So that might be one reason you might want to use a relative elevation grid. You might use it as an independent variable in a statistical model that you're doing. Another might be landscape analysis. Another way that I've used relative elevation is for creating landform classifications. So if we go back again, you know, we might break up these hill slopes into certain segments and call, you know, a certain segment maybe from 50 to 70% as a side slope or something like that. So it's a good way for classifying landforms or just any type of landscape analysis. And you can probably come up with your own reasons for using a relative elevation grid. So we'll just you know, insert your own application there as to what things you might come up with. So what does it look like? This would be the end product. So if you get the data of this course, you can make this grid. This is, of course, it's a 3D representation of a landscape. And it's broken up into 10 equal interval classes using relative elevation. So this top color or category here might be, you know, the high spots or the summits or whatever you might want to call them, upper shoulder, lower shoulder, that type of thing. And you can mess around with the classifications yourself. So this might be an example again of that landscape analysis where you're coming up with landform categories. But I thought I'd show you what it looks like in the end to know, you know, first of all, whether you're interested in watching the rest of this, and second of all, to kind of see where we're headed at with this relative elevation and what it looks like. So what's the trick? because the title's called Tricks to Creating Relative Elevation Grid. Well, the trick that I've come across that seems to work pretty well is do your analysis from a watershed or a watershed basin perspective, or using basin statistics to figure out the size of your area for the relative elevation. And I'll show you why this is a good idea. So here's just an arbitrary watershed, and then you can see the stream network within the watershed. And so some of you are probably familiar with drainage basin statistics, things like drainage density and that sort of thing. So the first thing you want to do, so maybe you just have a small area that you're interested in doing a relative elevation grid on, but you might want to kind of back out and look at the bigger picture or the landscape from a watershed perspective. And the first calculation, so we're going to do some basin statistics first to come up with our radius that we want to use for our relative elevation grid. So first you kind of have to go through some drainage basin statistics. So you might download the polygon for the watershed basin and download the stream network if you have that available. A lot of states have that GIS data available now. And you want to calculate the total stream length and the area of the basin. So some of you may already know how to do this, but if not, to get your stream length, you want to right-click on streams over here in your table of contents. And if you don't already have a field called length, then you'd want to create that field. And to do that, I don't have that as a screenshot here, but to do that you would go to this drop-down menu on the table and add a field. And you'd want to add it as a numerical field. A double field type is a good one to use. So once you've got your length field, you right-click on the length field and calculate geometry. And it's probably going to default as a length since you're using a line shapefile. And so you want to leave this at length and change that to kilometers. So we're going to do the thing with relative elevation and creating these grids is you want to kind of be familiar with your projection, datum and projection, and map units and that sort of thing. We're dealing with UTM coordinates, and so we're going to be using the metric system, or meters, kilometers, that sort of thing. So we're going to change this to kilometers, and we're going to calculate the geometry, and then it'll fill in the length segments of all of the stream length. So if we go back here, so each of these lines now for the streams has a length associated with it. And then the next thing you want to do is total up all of those lengths. And so to do that, you can again right-click on the length field in the attribute table, and then get the statistics of that field, and you can get the sum of the length in kilometers. So the total stream length for those streams that we just saw is 206.84 kilometers. So we'll write that down, make a note, 206.84 kilometers. So we've got the total stream length within the drainage basin. Okay, so the next thing we want to do is calculate the geometry for the basin or watershed. We want to get the area. So we right-click on the watershed polygon. And if we don't already have a field called area, depending on where you got the shapefile from, you can create one again by going to the drop-down, add a field. Again, you want it to be a numerical field, a double type. And once you have the area field, you right-click on it, calculate geometry. It's most likely going to default here to area. Again, you want to keep in mind your units, and you want to use the same units that you used on the length calculation that we just did. So down here you want to pick square kilometers. You hit OK, and it'll give us, in this case, a basin area of 220.62 square kilometers. So again, we write that down, put it in our noggin, and remember that so we can figure out the drainage density. So that's what we do next. So to find drainage density, you take the total length of the streams within the basin and the area, and you divide. So you've got 206.84 kilometers divided by 220.62 squared kilometers, and the answer you come up with is 0.94. So that is actually the distance, the average distance between streams. So we want to calculate half of that, or the length, what's called in basin statistics. We want to calculate the length of overland flow, which is half the average distance between the streams in the basin. So the reason we want to do this is because this is the average area from a summit down to the floodplain. So half the distance between two streams, and we can get that from basin statistics by calculating the length of the overland flow. So we're interested in what this average distance is right here. So when we go to calculate relative elevation, we can use a radius that's about the right size from a hilltop down to the bottom. So this one is a little more complicated of a statistic to run, but not too bad. So here is the formula. So you can see it here. This is where our drainage density comes in, so that's why we had to calculate that. And so run this calculation and we come up with 0.48 kilometers. So that's the distance from the average distance from here to here within the watershed is 0.48 kilometers. So that's the trick. That's the radius that we want to use to create our relative elevation. And you can come up with your own arbitrary radius, or you might have another way of doing it, but I found this to be a good way because one, it's not arbitrary, it's kind of more objective, and can kind of explain why you used a certain radius, but it's also makes sense because it will capture all that's going on in terms of relative elevation from the summit down to the floodplain. So we come up with 0.48 kilometers. So now we can calculate our relative elevation. So that's the first thing you want to do, is do some basin statistics to get your average distance from the summit down to the floodplain within the drainage basin. And so relative elevation, then we're going to use the neighborhood statistics in the spatial analyst toolbar. So you need ArcGIS in the spatial analyst toolbar to run this part. So we also need a DEM, a digital elevation model of the particular basin that you're in. So again, a lot of states have this data of polygons for your drainage basins, stream networks, and digital elevation models you usually can find for most areas that you're working in, especially in the United States. Okay, so get your digital elevation model for your watershed, and we're going to run a neighborhood statistic to create the minimum value within our 0.48 kilometers, and we're also going to calculate the range or the relief of elevation values within that particular radius. So first things first, we want to grab the digital elevation model, or the DEM, and we want to go to Arc Toolbox and go to the Spatial Analyst Tools, go to Neighborhood, and then Focal Statistics. So we double click on that. Our input raster is going to be our DEM, or digital elevation model. We want to say where we want to save it at, and then I prefer a circle instead of a rectangle as your radius. And then here's where we want to enter in our drainage basin statistics that we came up with. And so my map units are in meters because, again, it's UTM coordinates. And so I'm going to choose map here for units in 480 based off our statistics that we just ran. So the first one that we want to run is a minimum grid. So it's going to go through, it's going to take that radius, go throughout the raster grid and find the minimum elevation within that radius and populate the raster grid cell with that particular minimum value. So that's the first step. Then we want to figure out relief. This could be used as a relief grid, by the way, and it's also a good idea. You know, this course could have just as easily been called Tricks for Creating a Relief Grid. I would do the same thing. So this is kind of a byproduct of relative elevation, but also a useful grid to use in your models and whatever else. So again, you're going to use the DEM. So we're using neighborhood, focal statistics, and the spatial analyst tools. Input raster is your DEM. Again, save it somewhere, call it relief. Use a circle for a neighborhood, and again 480 map units. And this time our statistic type is going to be the range. So the range of elevations within that particular radius, which is also relief. Now that we have the minimum elevation and the relief, we can go ahead and calculate relative elevation now. So now we're going to use the Raster Calculator in ArcGIS. So again, you need the spatial analyst extension and go to Map Algebra, Raster Calculator. And so the formula that you want to put in here is to get relative elevation is the DEM minus the minimum. So it's going to do that first because we're going to put that in parentheses. And then we're going to divide by relief. And it's going to be scaled from 0 to 1, where 0 in a field means it's the lowest spot within that radius, and 1 means it's the highest spot. You could also take this, if you don't want it scaled in between 0 and 1, you could also add on here a times 100. And it will make it so it's between 0 and 100%. But that's up to you. And this is what we come up with. So now we have, I broke this particular grid up into 10 equal interval classes. So this dark orange color is the low spots within the radius. And then the higher blues would be your highest spot within that radius. So again, you could use this for modeling purposes. You could use it as an independent variable. Another example I didn't think about earlier would be maybe if you're a biologist and you're studying a certain plant type or a certain habitat. It might be that they're found at certain elevation ranges. So this might be another application for this. And then here we're back to our original that I showed you. So I did this in ArcScene. I brought in the DEM and then I overlaid this relative elevation grid using the DEM to pop up or make it 3D. And so again, you can mess around with a number of classes, but you know, from relative elevation, you can, you know, here's your high spots. Again, maybe upper shoulder, lower shoulder, side slope. You know, you can change. It doesn't have to be 10 categories. You can, you know, maybe use a natural breaks and do 6 or 7. You know, it's kind of up to you on that. But this is what the final output would look like. And so again, if you want the data for this, you can go to our website, which there will be a link to that here on YouTube and in the description there. You can go to our website and get the data, and then you'll also get the PowerPoint, so you can see on, you know, you can open it up on your own computer and see the screen better than you're seeing it here. And then if you have any questions as well, if you purchase the data used here for this course, then I would be more than happy to answer any questions that you might have. You know, prefer that you would email them at cagoings@rollinghillsconsulting.com. My number is also 319-461-7427. So if you are interested in this and you want to kind of go through it yourself, you can get the data from me, and then you can also ask me any questions if you do that. So I hope this was helpful, and I hope you got something out of this, and there'll be more courses to come. So if you'd like to subscribe to the YouTube channel, that will keep you informed as to when the next video is posted. So thanks for watching.